So pretty much what we're going to talk about is carboxylic acids. We already encountered them before. Remember, we were talking about the oxidation of alcohols, how alcohols can be oxidized sequentially, for instance, primary alcohol, right? So let's say we have ethanol. Does that make sense? If we oxidize ethanol, we're going to get acetaldehyde. Making sense? So that's oxidation. And if we oxidize acetaldehyde, we're going to get acetic acid, vinegar. Am I making sense? So I want to highlight, we talked about it last time, that how do you know that oxidation went through? There is only one carbon-oxygen bond in ethanol. There are two carbon-oxygen bonds in acetaldehyde, and there are three carbon-oxygen bonds in acetic acid. Okay, good. So formally, the names used, you do it this way. So methane contains one carbon. Clear? So you replace E with oic acid. This is the proper standard IUPAC name. For first four acids, we have common names. Formaldehyde. So remember formaldehyde, acid. So formaldehyde, formic acid. Acetaldehyde, acetic acid. Propionaldehyde, propionic acid. Butyraldehyde, butyric acid. Okay? You're going to find them in different compounds. Well, vinegar, yes. Okay, formic acid, ants. Propionic acid, oh, I'll tell you the story about propionic acid, not only corn. And butyric acid is found in butter and actually determines, to some extent, its taste. Okay? Now you can see that the number of carbons progressively increases, okay, from 1 to 4 in this particular table. But there's another thing. I want you to identify this, the functional group, the carboxylic group, that produces that acidic character. Okay? So in each of these images that you see, in each compound there is a carboxylic group. All good so far? So, acids, carboxylic acids, are weak acids. Does that make sense? As a matter of fact, out of all of these acids, the strongest is the formic. Okay? It's still a weak acid, but we can do the arrow and write down that acid strength decreases as you increase the number of carbons. Sounds good, everybody? Okay. So if they are acidic, it means that when they dissociate in the aqueous solution in water, they should produce hydronium ion. Let's explore why this is happening. If you look at take a look at periodic table, remember the electronegativity story that we talked about? How different elements have different ability to attract electrons. So the highest electronegativity is fluorine. Second highest is oxygen. So When you look at this group, the carbonyl group in carboxylic acid, this carbon is connected to this oxygen by 2 bonds, and oxygen pulls the electron density towards itself. Okay? They're not transferred, they're just pulled, which means there's a pretty substantial positive charge on that carbon, as well as partial negative charge on oxygen. But not only this, hear me out. This oxygen right away pulls electron density from the carbon and from the hydrogen. Okay? Which means that this bond is very polar. Okay? Means that it can be broken in aqueous solutions, and this hydrogen may dissociate. Okay, now you may notice that these are 2 groups that we've already talked about: hydroxyl and carbonyl. We usually don't separate them because they don't act independently. So we say that an acid is a carboxylic group, which consists of a carbonyl and hydroxyl. Similarly to aldehydes, the less carbons you have, the more soluble the acids are in the water. Why? Because remember, the oxygen of the carbonyl group is a partial negative charge, while the hydrogens of water have a partial positive charge, so hydrogen bonds. Similarly, the hydrogen of hydroxyl group in carboxylic acid is a positive charge, and the oxygen in water is a negative charge, so another hydrogen bond. Clear? 1 to 5 carbons, these acids from metanoic to pentanoic are soluble in water. Okay, because 5 carbons is still not nonpolar enough. When you start increasing the number of carbons, the solubility is reduced. And I'm going to give you one example, folks, if my memory serves me well. I believe stearic acid has 18 carbons. Okay? Does that make sense? It's one of the main components of butter. It's a fatty acid. It's not soluble in water. Okay? So, already at 6 carbons, solubility drops. This is the benzoic acid formed by addition of carboxylic group to the benzene ring, which is also not very soluble. There are 6 carbons there. Okay, good? Acidity. So this is an interaction of ethanoic or acetic acid with water. You can see that this this hydrogen dissociates from the molecule of acetic acid, right? Binds to molecule of water, forming hydronium ion. Does that make sense? You see that there are 2 arrows here, showing that this reaction does not go to the completion. Carboxylic acids are not fully dissociated in water, therefore they are weak, and there was something else very smart I wanted to say, and I forgot. So they weak electrolytes, and they weak acids, because they don't completely dissociate. Sounds clear? Now, one of the reasons, and this is going to be a very, very tangential introduction, why acids, carboxylic acids, can actually dissociate, like what facilitates. So when you have an ion like this, you can write it this way. Agreed? Or this way. Okay? So these are called the resonance structures. What it means that at any given moment, if you would somehow become as small as an atom and got in the solution and look at an individual molecule of acetic acid, it would exist in one of these two states. And the probability of it being in the left or right, they are identical. So these are resonance structures. Sometimes they are pictured this way. The dashed line shows that the electrons that form one of the bonds, they kind of delocalized over those oxygens. That stabilizes the ion, the delocalization. Okay? So since these are acids and they dissociate in aqueous solution, they can form a salt. So if you will run the reaction between a carboxylic acid such as formic acid with sodium hydroxide, hydrogen of the carboxylic acid will react with OH minus group hydroxide anion of sodium hydroxide, forming water. Okay? And soluble salt of sodium. Okay? So, how do you form the name of the anion? So you replace oic acid with O8. Methanoic acid, methanoate. Okay? Reasonable? Excellent. Salts of certain carboxylic acids can be used as preservatives, food preservatives. They're pretty safe. Salts of certain carboxylic acids can be used as soap. And this is what we're going to be doing next Monday. We're going to be making some soap. Okay? So at the room temperature, the salts of carboxylic acids, the so-called carboxylates, okay, they're solid. They dissociate in water if they are soluble. For instance, most acetates, salts of acetic acid, salts of vinegar, they are soluble, practically all of them. Okay? So, sodium propanoate and sodium benzoate, they do serve as food preservatives. But I wanted to highlight this. So what you see here is monosodium glutamate. Okay? The infamous MSG. Does anyone know what glutamate is, or glutamine? Well, glutamic acid. So if you will replace the sodium with hydrogen, okay, you're going to get glutamic acid. Am I clear? It is an amino acid. It is normally found in proteins, in any living organism. So glutamic acid isn't something nefarious. Make sense? Sodium salt of glutamic acid isn't something nefarious too. The problem is glutamate serves as a neurotransmitter in different parts of the nervous system. And it may explain why some people I can't, by itself, monosodium glutamate isn't a problem. Some people have high sensitivity to monosodium glutamate, like me. If it is in the food, I'd rather not. It stimulates the motility of the intestine, which means I'm going to have some diarrhea, okay? I'm not going to vomit. It's not going to be super uncomfortable. It's just, I got no. And the problem is some cuisines routinely use it. So I have very conflicting take on this. I love Japanese noodles, known as ramen, but they use MSG all the time. So I have to do like a compromise and ask myself, do you want them that much? And the answer is usually yes. But I have to take some precautions. Okay, does that make sense? So a lot of carboxylic acids are the parts of metabolic processes. For instance, glucose, when it is broken down during glycolysis, forms pyruvic acid. Okay? So, this is your carboxylic group. Right? If pyruvic acid cannot be properly processed in the process of aerobic respiration, pyruvate is going to be fermented into lactic acid. Okay? Does that make sense? If we can properly metabolize pyruvate, it will eventually enter Krebs cycle. Okay? And the first classic intermediate of Krebs cycle is citric acid. So what I want to highlight here, this is called tricarboxylic acid. This is one carboxyl group. This is another carboxyl group. This is the third carboxyl group. Okay? So this is why we call it 3-carboxylic acid, or the Krebs cycle. Names, check this out. Citric acid cycle, because that's the starting point. Krebs cycle, in honor of Hans Krebs, I don't remember his second name, Hans Krebs, who discovered it. Or sometimes it is called TCA cycle, where TCA stands for tricarboxylic. Okay? Makes sense? And citric acid is oxidized and eventually produces fourth step of Krebs cycle gives you succinic acid. It is oxidized to fumaric acid. It is hydrated to malic acid. And malic acid is oxidized to oxaloacetic acid. You can see that all of them are dicarboxylic acids. That makes sense? Everyone? Just as an example. So now we're going to talk about esters. Esters are effectively the derivatives of an alcohol and carboxylic acid. Does that make sense? So, turns out that if you chew on the bark of a willow tree, it works as an antipyretic, and it works as the analgesic as well. So basically, turns out that the compound called salicin, isolated from the bark, when you eat it, it is converted into salicylic acid. It works as an anti-inflammatory, antipyretic drug, but it also a pretty strong irritant for your stomach lining. So the company Bayer There's a pretty checkered past. They did invent aspirin, as well as produced a bunch of chemicals that were used during the Holocaust. But Bayer figured out that if you modify this acid by forming salicylic acid, the ester, it's less disruptive for the stomach. So this is how it works. So imagine we have acetic acid. You with me? Okay? So what I'm going to do, I'm going to replace that group with an alkyl, like methyl. Okay? Good? So what do we call that? You treat this part as the anion of carboxylic acid. So this is ethanoic or acetic acid. Clear? What do we call an anion? What do we call salt? We call it ethanoate or acetate. Am I making sense? I'm not finished, but does that make sense? That nomenclature, that transition. All good? So now when we talked about salts of these acids, the first word was the name of the cation, like sodium. In this case, instead of the cation, we name that hydrocarbon that sticks out. So, what do we call CH3? It's methyl. Making sense? Let's name something. Formic acid. Methanoic. Sounds good? So here we have the ester. This part comes from the acid. This part comes from the alcohol. So 2 carbons. What is the name for a hydrocarbon? Saturated hydrocarbon with 2 carbons. Starts with E. Ethane, right? So we go from ethane to ethyl. Okay? Good? And then formate. Or methanoate. Does that make sense? Reasonable? Okay. So this is the salicylic acid story. This is salicylic acid. So this is the acidic group. This is hydroxyl group. Remember that hydroxyl group is characteristic for alcohols, right? Does that make sense? Now, when hydroxyl group is attached to benzene ring, it forms a molecule that we call a phenol. So it's basically, property-wise, it's a combination of the acid and the phenol. Okay, make sense? So when you mix salicylic acid with acetic acid and provide some, well, acidic catalyst, basically adding sulfuric acid, what happens? Which would be leaving group? This OH group departs. This hydrogen departs. Okay? And you have an ester where alcohol component comes from salicylic acid and acidic component comes from acetic acid. Sounds good?
So the salicylic acid is basically just a combination of the phenol and carboxylic.
And carboxylic group, yes. Yes. And it shows how by slightly adjusting the chemically modifying stuff, we can turn some natural compounds into more and more efficient drugs. Okay? Can you excuse me for a second? I apologize.